So this is a tank question, compartmental differential equations question, example, and it's going to end up being a little bit difficult because of the integration, not because of the setup. So let's read through. You got a half full 10-liter tank. Okay, that means it initially contains 10 kilograms of salt. So at t equals 0, the volume is 10. It's half full 20-liter tank. And at t equals 0, the kilograms of salt in the tank are 10. So this initial condition, that's going to give us our constant when we integrate. So a pipe pumps in saltwater concentration at a rate of 6 kilograms per liter. That's the concentration of the inflow into the tank, but it's not a constant rate. Okay, this is the new thing. Normally, it is a constant rate, and we just take kilograms per liter times liters per minute. The liters cancel out, we get kilograms per minute. But now it's not a constant rate. So let's think about that for a second. And I'm going to relate things to area. If I'm calculating the area and it's a rectangle, I just multiply height times length. If it's a constant height over that length. If it's not a constant height over that length, I integrate the height over the length. So the same idea here. I normally would multiply, if it's a constant, kilograms per liter times liters per minute if it was a constant, but it's not a constant, so instead of multiplying, I'm going to integrate. So, okay, let's look at this function. It's not a constant rate, then what is it? At first the tap is off, it's 0, it's turned up to its full rate of 8, and then back down to 0 at 4 minutes. So it's 0, 8, 0. So the flow rate of brine, salt water, in liters per minute into the tank is given by this upside down parabola. See, if I make t equals 0, it's 0. If I make t equal to 4, it's 4. If I look at, since I made it a parabola, the highest point should be the middle at 2. If I plug 2 in here, I get 2 times 2 times 4 minus 2. 2 times 2 times 2, 8. So this is the graph of the flow rate in, up to a maximum and down to 0. Now, there's two places here. At 1 minute, the flow rate in is 6. At 3 minutes, the flow rate in is 6. So those are the two places where the flow rate in is equal to the flow rate out. Before 1 minute, it's less than, the in is less than the out. After 3 minutes, the in is less than the out. In between 1 and 3, the in is greater than the out. So in between 1 minute and 3 minutes, the flow rate in is greater than the flow rate out. So the volume should be going up. The volume should be going up in between 1 and 3 and down outside that region. Okay, now we know what the flow rate in, and our normal sort of MO then for these things is we call Y prime the kilograms per minute, and we get that as in kilograms per minute minus out kilograms per minute. And the kilograms per minute are always kilograms per liter times liters per minute. Concentration times flow is what we do. And the out, this is the out here, the concentration is given by Y kilograms, that changes, over the volume, in this case, that changes, times 6 liters per minute. It's a constant. 6 liters per minute is the flow rate out. That's a constant. So here we've got the flow rate out. The in is usually concentration of in as a constant times flow rate of in as a constant, but the flow rate in is not constant. So we're going to have to integrate it. Now let's finish reading the question. The tank is well mixed and the outflow drains at a rate of 6 liters per minute. That's this 6 liters per minute. The volume's not constant. What is the volume? Well, okay, there's where we said we had to integrate. I know initially the volume is 10. So I'm integrating the flow rate. That's flow rate in minus flow rate out. Normally we just multiply flow rate in minus flow rate out, multiply that by time, but now I'm integrating it over time because this in minus out flow rate is not a constant. So when I integrate it, I'm just going to I'm going to multiply that bracket through so that my integration is easier. When I integrate it, I get a plus c. How do I get the constant? Initial conditions. The initial volume is 10 because it's a half full 20-liter tank. So when I make t equal to 0, the volume is equal to 10. So here's my volume formula. Now I've got the volume that's going to go underneath for the kilograms, y kilograms divided by v liters for the concentration in the tank, which, because it's well mixed, is the concentration of the effluent, of the outpipe. Let's take a look at what the volume is. I knew it started at 10. We knew it was going to drop until 1 minute. Now I'm at the top part of that parabola. Then it's going to increase until 3 minutes. Now at 3 minutes, that's when I've turned it up to the maximum, and I'm turning it back down. At 3 minutes, the flow rate in is 6 and the flow rate out is 6. And then it's less than 6, so the volume starts to drop. This inflection point is right at the tip of the parabola. Increasing, 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 start to decrease. So there's my inflection point. Okay. The volume formula makes sense. So I'm going to call y of t the amount of salt in the tank at time t. How many kilograms of salt are in the tank 3 minutes after the start time? All right. Let's follow through the regular procedure we do. In is kilograms per liter times liters per minute. Liters per minute is not a constant anymore, it's a function, minus, again, concentration. Our concentration is kilograms per liter. The liter is not a constant, times this 6. That 6 is a kilograms per liter, a concentration. So in and out are concentration times flow rate, concentration times flow rate. So y prime is in kilograms per minute. It's a first order linear differential equation. So we know in principle we can solve that. Let's just put it into the y prime plus py equals q. Get our integrating factor, which is e to the integrate p. So our plan is do this integration, get u, multiply all three sides through by that u value, integrate both sides. The left-hand side is always going to integrate to be y times u, and the right-hand side integrates to be whatever it's going to be integrate to be. Our problem here is that the initial integration, while not impossible, is kind of hard. You'd have to do partial fractions on this, and then the partial fractions will give you a piece with a ln in it and a piece with an arctan in it. It's going to be hard. And then whatever I get, I'm going to end up multiplying this by the piece with the ln and the piece with the arctan, and I have to integrate that right-hand side with the u on it. That's also going to be hard. So I'm going to change gears here. This is not what I would do on a quiz or a test or something, but this is what I would do in real life. Remember, the thing I want is just how many kilograms of salt are in the tank 3 minutes after the start time. So I just want a number. So I'm going to put this back. I'm going to move that back over. So I have y prime is equal to some function of t and y. So I've got y prime, that's a slope formula. Plug in a t and a y, and I get the slope. I'm going to do Euler's method on this. So the new y is equal to old y plus h y prime plus hf plus the h times the slope, Euler's method. So let's pull out a spreadsheet here. I want a pretty good answer, so I'm going to make my step size 0.01. My initial point, I start at the point 0.10, that's given. At t equals 0, there's 10 kilograms. 0 and 10, I plug into the slope formula. I plug into the slope formula. I plug in 0 and 10 into the slope formula, get the slope, multiply it by the step size, so that's hy prime, and my new y is equal to my old y plus hy prime. There's my new y. How do I get all the new t's? Well, the new times are just take the old time and add 0.1, add 0.1, add 0.1. They're all step size 0.1 apart. So at this stage, I've calculated my new y, old y plus hy prime. Now I've got a time and a y. I plug it into this hy prime formula again, this y prime formula again, and calculate hy prime. And again, new y is equal to old y plus hy prime. Euler's method all the way down, and that gives me these points that are supposed to be approximately on the curve. Because I chose a step size of 0.01, I'm confident that this is not going to be too bad. So here's my graph that I get of all these points, all the way from 0 to 4. Remember, our equation kind of stops at 4 because that's when the tap is off and we don't know what happens after that. So the initial value is 10. There's 10 kilograms. We start adding salt water. It goes up. It looks like it peaks around 3. Oh yeah, that's actually what I want, right? How many kilograms of salt are in the tank at time 3? I can see that it peaks here, but I want to know what it is at 3. So let's just go all the way down and find 3. There. This is what I'm looking for. When t equals 3, there's approximately 54.17 kilograms of salt in the tank. Is there exactly 54? No, because we solved it numerically, but probably super close. Again, this is not how I would solve this exactly, or solve it on a test this way or quiz, but it's a way we can get a real answer.